Hi, thanks for joining me. Today I've got a fun differential equation I want to show you. It's this guy here, dy dx equals tan squared of x plus y. And what we want to do is solve this differential equation. Now, why is this a cool differential equation? Well, firstly, it's not particularly obvious as to how we go about solving this thing here, because it's certainly not of the form dy dx plus f of xy equals g of x, so in the form where we could use the integrating factor. And also it's not separable, at least how it is at the moment, because the right hand side is not of the form f of x times g of y. So those are generally the techniques we use to solve first order differential equations, and we can use neither of them. But I'm going to be showing you a cool way to solve this differential equation. If you want to have a go at trying to solve this differential equation, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the key to this is perhaps noting that this right hand side, tan squared of x plus y, it would be a lot nicer if this input here, x plus y, was just a single variable. So that's exactly what we're going to do. We're just going to make it a single variable by just essentially doing a u substitution. So generally we do u substitutions with integrals to help solve integrals, but here we're using a u substitution to help solve a differential equation. Okay, so let u equal x plus y. So then that means, of course, if we just differentiate both sides of this equation here with respect to x, we get that du dx is equal to 1, because the derivative of x is 1, and then the derivative of y is just dy dx. Okay, now what we want to do is plug this back into this thing here. So dy dx now is just du dx minus 1. And that equals tan squared of x plus y, but x plus y is just u. So this is tan squared of u. Now we can just add 1 to both sides. So that gets rid of the minus 1 there and puts a plus 1 there. So now we've got a nicer looking differential equation. Du dx equals tan squared u plus 1. But now in fact we can use our trigonometric identity that tan squared theta plus 1 is equal to secant squared theta. And just using that with theta equals u. This thing here equals secant squared of u. Now what we want to do is solve this differential equation here. Du dx equals secant squared of u. Let's do that. Okay, so we have du dx equals secant squared of u, and now this is indeed a separable equation, so we can write this now as 1 over secant squared of u. So if you divide both sides by secant squared of u, on the left hand side we get 1 over secant squared of u, which of course is just cosine squared of u, and then du, and that's just equal to dx. And of course, you can't really multiply this thing here, but it acts like a fraction. It's not a fraction, but it acts like a fraction, so we can kind of multiply by dx. And anyway, we get this thing here, so the integral of cos squared u du is equal to the integral of dx, and of course we've got a plus c. Now this right hand side is nice and easy to evaluate, it's just x plus c, so let's write that in there. Now this left hand side we've got to do a bit of work on. The integral of cosine squared u du, we're just going to use our double angle formula and recall that cosine of 2 theta is exactly the same as 2 cosine squared of theta minus 1, sorry. So cosine of 2 theta is equal to 2 cosine squared of theta minus 1. So plugging that into this thing here, cosine squared u then is cosine of 2u plus 1 all divided by 2. So this is equal to a half the integral of cosine of 2u plus 1. That's du, and that of course equals x plus c. Now this thing here we can just integrate. Integral of cosine of 2u is going to be a half sine of 2u, so multiplying it by this half here, we're going to get a quarter sine 2u, and then this plus 1 here becomes a u, and then this half here makes it plus u over 2, and that equals x plus c. So you get a quarter sine of 2u plus u over 2 equals x plus c, and we're almost done. The last thing we need to do is just plug in what u was, and u, remember, was just x plus y. So let me just rub this top bit off. We can just write down our solution now. Our solution is the curve, a quarter sine 2x plus y plus x plus y over 2, and that equals x plus c, where c is an arbitrary constant. And that is our solution to the differential equation. A nice little substitution at the start, which essentially made the differential equation nice and easy, and then once we've done that substitution, we could apply the techniques that we're familiar with. Anyway, I hope you have enjoyed this video. Thanks for watching. I'll catch you in the next one. Have a great day.